Hello, Stats class. Here's the beginning of a new chapter. It's chapter 13, and it's called Analysis of Variance. That's often abbreviated as ANOVA or ANOVA. And as we talked about in the warm-up a little bit, ANOVA is for comparing means of multiple populations. Well, that's interesting because we're talking about the means, and yet it's called analysis of variance. Variance, remember, is a measure of spread. So it compares these means by analyzing variances, which is the standard deviation squared, or a measure of spread. So I introduced this a little bit in the warm-up, and I'm going to just talk a little bit more about how that works, but we're going to get the technical part tomorrow. The calculations are tomorrow. Tomorrow. So how it looks, we look at variation two ways. There is such a thing as good variation versus bad variation. And the good variation is the differences between the treatments, because that's what we want to find. We want to find differences between our populations. Or if it's an experiment, that would be treatment. Bad variation is the variation that gets in the way of seeing those differences. So if there's a lot of variation within each data set, that's bad. So the bad variation, I didn't write the word variation, but bad variation is about differences within each population or treatment group. All right, so we saw some box plots in the warm-up, and I'm going to do it again, except I'm going to do 3 populations because you can have as many populations as you want. Here are some box plots, just as an example, and let's say there's no overlap at all between those first 2, and maybe the third one is down here with a little bit of overlap. This is a good example because you can really see that there's a difference between these populations. There's no overlap. This one's in the middle, but there are definitely 3 different things. The difference between is large. Compared to the difference within. In other words, the good is more than the bad in this case. On the other hand, sometimes we get data that looks like this. Let's make some longer box plots. And let's do a lot of overlapping. Here's an example where there is a difference between the means, but it's kind of clouded by this widespread in each data set, so that makes it harder to tell for sure, and this would be less likely to come out significant. So this is the difference between small compared to the difference within. And so this one's likely to come out significant difference between the means, which means we would be rejecting a null hypothesis, which we haven't even really talked about yet, but the null would be that the means are equal. And this would be not significant, most likely, but it might be. It's just kind of on the border the way I do it. So it's hard to say without the numbers, but more likely to be not significant. And don't reject not enough evidence, basically. So that's where we're headed with that. We will learn on tomorrow's lesson how to do the calculations that will actually cause this to happen. But I wanted you to see where we're headed. For today, all we're going to do is that just a little bit of intro, plus we're going to do conditions and hypotheses. So we're going to do the first 2 steps of the 4 steps today, and then we'll come back to step 3 tomorrow. And you really already know how to do step 4, which is the conclusion. So that's kind of nice. So today, we're going to do state and plan. So state would be the hypotheses. How do you write hypotheses when you have multiple populations? Well, you've already seen that with chi-squared if you had multiple populations, except that was proportions. So remember, we talked about with chi-squared, you could do P1 equals P2 equals P3, but mostly we write in words instead. Here, we're going to do mu1, because we're saying that means of populations. Remember, means of multiple populations is our goal here. So we're going to do mu1 equals mu2 equals mu3 equals, how many do you want? I've seen ones with 7 or 8 of these, and I've seen others with only 3. So you can have as many of these as you need for your situation, as many as you want. Or you So just like with chi-square, we're breaking free of the restriction of having to have only 2 populations, and now we can have lots of them, and that's fun. And then the alternate is also going to remind you of chi-squared, because the alternate is the same idea as chi-squared with proportions. We don't need all of them to be different. We just need at least one to be different. So at least one population mean is different. That is our alternate. We're just going to write it in words. We don't write it with not equal signs because it could be that 1, 2, and 3 are the same, but 4 is different, or something like that. All right. And then don't forget to include context in your state step. You would always want to say what those mu's stand for. So mu1 would be the mean what of what, and this is where you put your variable, what is it we're measuring, and this is where you put your first population. And then you would do mu2 is the mean what of population 2, and so forth. So you always have to say which population is which, and say it's the mean of, the mean number of flowers, or the mean weight, or the mean whatever it is that you're measuring. Okay, so hypotheses are actually pretty easy. It's like the difference of 2 means, except there's more than 2. And then let's talk about conditions. Plan is going down here. The name of the test is an ANOVA test. I don't think I even need to say that, but maybe I'll do this for an ANOVA test. And everybody in the stats community just calls it ANOVA. They hardly ever write out analysis of variance. But anyway, there are 4 conditions. That's not so bad. We've seen situations where there's 5, right? So it is only 4 conditions. Tonight's homework is just going to be writing hypotheses and checking conditions. That's all you have to be able to do. You probably could have guessed that we're going to start with random. In fact, all 4 of these conditions you've seen before in other places. The first 3 are very familiar, and then the 4th one we've only seen once, but that's okay. Random, you have to have separate random samples from each population. There's usually more than 2. I suppose you could do an ANOVA test on 2 means. It would be the same as a difference of 2 means. Same result. Samples from each population, or you have randomly assigned treatment. In an experiment, that happens a lot. You probably could guess the second one. It's normal. When you're looking at box plots, it's hard to tell if they're normal. You're just looking for, are they not skewed? Or maybe you're looking at dot plots or histograms or something like that. You're just checking to see if they look not skewed. So either the populations are normal, approximately, and you would tell by checking the graphs, like we've done before, not too skewed. Or since this is means, we can still do what we've done before with the n, or you could have sample sizes that are large. If n is greater than or equal to 30, then that's good enough. We're going to use the 15-30 rule here also. If it's between 15 and 30, we're going to be not too picky about the skewness. And if it's under 15, it needs to be just about perfectly symmetric. But yeah, just check to see if they're not too skewed. I guess we could do normal probability plots, but mostly I've seen them give you lots of dot plots or lots of histogram or lots of box plots, and just say, look at these. Do they look good to you? Yeah, sure, they look fine. So that's the usual way. Independent, same thing as we've done before. If it's an experiment, then the randomly assigned treatments covers that. If it's a sample, then all the sample sizes of all the different samples have to be less than 10% of each respective population. Or, like I just said, you could have randomly assigned treatments covering that. The fourth one will remind you of the slope chapter, because the fourth one is equal variances. And we've seen that before in slope land, and here it is again. Interesting that we're testing using variances, and that test really only works if the variances are about the same. So these box plots are all about the same spread. These are about the same spread as each other, but not the same as these. That's what you're looking for. Do they look like the populations or the samples are about the same spread? Approximately the same spread. And you can just tell by looking at the plots. That's one way. It's kind of the informal way. Or there's another way, if you're not sure, there's a rule of thumb or just a general guideline that you check the biggest standard deviation and the smallest standard deviation, and those would be the sample ones because we don't know the populations. So the biggest standard deviation of a sample has to be less than twice as big as the smallest one. So another way of saying that is that the biggest sample standard deviation divided by the smallest of all the populations, or samples technically, because we don't have the populations less than or equal to 2. So you could either divide them and see if it's less than 2, or you could just think, well, if it's twice as big, that's bad. If it's less than twice as big, then we're okay. So believe it or not, that is all you have to do for today's work. Tomorrow we're going to get the hard part, which is the calculations. How do you compare, how do you measure good variation? How do you measure bad variation? How do you put that together into a test statistic? We'll do that tomorrow. And today's homework is actually pretty short. It's numbers 1 through 6. And it's in the PDF that there is a link to. Actually, I'm going to show you this just for fun. Pardon me while I walk across the room to get this. I used to make packets. So like I make this little packet where this is your textbook for this week, and yeah, it's in a packet. You guys get the benefit of having full color on the PDF. So you'll have a PDF that is your textbook for this chapter, and I think I put the page number where the exercises are in the Canvas assignment. Or if I didn't yet, I'll do it now. So there you go. That's all you need to know for now.